So in this video, we're going to talk about power. So while we're always interested in voltage and current, the relationship of voltage and current, we're also interested in power, how much power is being dissipated by the circuit. Sometimes we're wanting to deliver maximum power. For instance, if you're into music at all, or I should say more than just music, if you're into like audio systems, if you've ever played around there's a concept of delivering maximum power to your speakers, because it's not the voltage or the current that makes the volume loud. It's the combination of those, which is power, and you'll see speakers rated in watts as far as how much power they can handle before you might damage them. And one of the things you want to do is you want to be able to deliver maximum power, and so there's something that's called impedance matching for speakers. But another thing that you might want to do is you might want to be reducing the amount of power, because if you think about a computer, for instance, the power that's being consumed by the microprocessor is actually a bad thing, because it generates a lot of heat. And that heat actually, the reason you have to have those big cooling systems or a fan or something, heat sink on a microprocessor, is that if it overheats, it can actually damage itself. Now, modern microprocessors have temperature sensors, and they will, in theory, shut themselves down before they damage it. But that would be an instance where we're trying to get rid of power in the form of heat. We're trying to dissipate it in a better way. So power is going to definitely be something we're interested in. Now, for power, we have a nice easy thing. We just have P is the symbol that we represent for power. And the units for power are watts, which is simply W. Now, what's very nice for us is that the equation for power is very simple for us. It is simply voltage times current. So that's how you compute the power that something is either absorbing or, quite frankly, delivering. Because if you think of a battery, unless you're recharging it, a battery is not absorbing power. A battery is delivering power to a device. But you calculate the power by saying what is the voltage across the component, and then what is the current going through the component, and that gives you the power that is either being absorbed or produced by the component. Now, real just quick, easy example here is that if a component has, let's say, 3 volts across it, and 2 milliamps through it, what is the power in this case I'll say it's dissipating. I need to really give you more information to know whether it's dissipating or generating power, but in this case I'll say it's dissipating. I'll just tell you that's what it's doing. And again, don't overthink this, of course. I mean, this is really just a very simple problem here. Power is equal to voltage times current, which is equal to 3 volts times 2 milliamps. Now, this is where you have to, again, be careful with units. Now, there's several ways to do these kinds of computations. I'll just write the answer down. The answer, if you do this on your calculator, however you do it, if you do it correctly, you wind up with 6 milliwatts, which isn't a ton of power. But we, again, have to be careful. I've seen people write 6 watts down before, which is wrong. Of course, it's 6 milliwatts. Now, if we want to think about a watt here, a watt is actually a volt times an amp. So a volt times an amp is what a watt is. So if I think about this here, I have volt and amp here, so that those units multiply together and give me watts. But then the M is still there, the milli is still there. So that's one way to think of it being 6 milliwatts, is that the volt and the amp combine together, because you can think of all these units just as multiplying. And so you have V times A times M, and then 2 times 3. And so the V and A give me the watts, and I'm still left with the M. Now, another way to think about it, of course, is simply just to do the actual computation. So there's a couple ways we could type this into our calculator. So we could do 3 times 0.002 if we wanted to type it in manually as far as what it is, because that would be 3 volts, and this represents 2 milliamps. So let me put here, this is in volts, this is in amps now. So I have volts times amps, which gives me watts, and so I wind up with 0.006 watts, and then of course converting it using engineering notation, I'd get 6 milliwatts. Again, there's lots of ways to think about this. Depending on your calculator, you might also enter this in as 3 times 2e to the negative 3, because it's milli, so it's 2 exponent negative 3. And that would give me, on my calculator, 6e negative 3, which of course is 6 milliwatts. So lots of ways to do that. I know I'm harping on this. I harped on it in the last video, and I'm doing it again in this video, but I just really get frustrated myself when I'm grading assignments and I'm seeing people make silly errors with their units. And units are very important. I'm going to date myself here. Many years ago, you guys were probably born after this occurred, but there was a Mars rover that crashed into Mars. We didn't successfully land it, and it crashed into Mars. And they determined the reason it crashed into Mars was actually an issue with units. They sent the wrong data to the landing craft as far as like how much thrust to burn or something of that nature, and they sent it because it was in the wrong units. So units are very important, and can actually, mistakes in units can cost lots of money. All right, so that equation for power, this power equaling current times voltage, this works for any device. So, and I know I wrote it current times voltage this time as opposed to voltage times current. It doesn't matter. So it's not just resistors. That works for any device. But now let's look specifically just at resistance here. So what about a power being dissipated by a resistor? So this is a special case. And the reason I'm looking at this is that there's actually other ways to calculate power that's being dissipated by a resistor. Now, first off, let me highlight something here. I say power being dissipated by a resistor. A resistor does not generate power. A resistor only dissipates power. So it can dissipate it in the typically in the form of heat if it's just a random resistor, but it can also be maybe there's light that you get from it, or something else that you get from the resistor. But a resistor only dissipates power. It cannot create power. If you can figure out a way to get a resistor to create power, come talk to me. So power being dissipated by a resistor. Well, I'm going to go back here and I'm going to write the equations we have so far. We have power is equal to voltage times current, and I know I switched it again here. But then we also have Ohm's law, which we talked about in the previous video, which is voltage is equal to current times resistance. So what we can do here is we can actually take this equation and substitute it in here. And so what we wind up getting is we could get power, and again, this is only for a resistor. In fact, I'm going to do a subscript P, subscript R for resistor to make sure to emphasize that. Well, I substitute in and I'd have I times R times I. Well, simple rearranging in some basic algebra gets me that power across or being dissipated by a resistor. Another way, instead of doing voltage times current, I could simply take the current, square it, and then multiply by the resistance. But we could also rewrite Ohm's law. I'm going to rewrite the power equation again. Again, I changed it for some reason. But we could rewrite Ohm's law is that current is equal to voltage divided by resistance. And then we could take this equation here and substitute it in for I. And so we get another formula that the power across a resistor, or being dissipated by a resistor, I should say, is equal to voltage divided by resistance times voltage, which is equal to V squared divided by the resistance. So we now have actually three ways to compute the power being dissipated by a resistor. So the power being dissipated by a resistor, we can go back and use our original way of computing power, which is just voltage times current. But we can also use the equation, we can also use the equation that it's the current squared times resistance, or that it's the voltage squared divided by resistance. All three of those formulas will get us the same answer. So let's look at one example here. And I'm going to do this one example here to show another way you can work with units. So suppose a resistor has 4 milliamps of current going through it. If the resistance is 5 kiloohms, what is the power being dissipated? I've probably spelled dissipated wrong every single time I've written it out here. All right, so again, not too difficult, or hopefully it shouldn't be too difficult. This is just computing the power. And somehow, I don't know if I erased that somehow, but my equation here for the voltage squared divided by resistance didn't get written down. All right, but in this problem here, this example, we can clearly see I'm given a current and I'm given resistance. So it makes sense that I would want to use this formula here, because I already have everything. I can just directly compute the power. So the power being dissipated by the resistor would be the current squared, so that's 4 milliamps squared, times 5 kiloohms. Now, we can type this into the calculator and get the correct answer, but there's also a way to do this without needing to even use a calculator. So, how are we going to do that? Well, I'm going to look here at the fact that this would be 4 squared times milliamps squared, because the units get squared as well, times 5 kiloohms. Now what I'm going to do is I'm going to write the units here, and I'm going to drop the amps and the ohms, because I know the units work out to be watts. But what I'm going to do is I'm going to keep the milli and the kilo, but I'm going to write it kind of in that scientific notation. So this would be 16 milli is 10 to the minus 3. And instead of saying square, I'm just going to write another 10 to the minus 3. Because if I do times 10 to the minus 3 times 10 to the minus 3, that's 10 to the minus 3 squared. Times 5 times 10 to the third power. Now, this is something that we're all familiar with, but we don't necessarily think about it this way, about combining things. We're all familiar with, I'll write it off to the side here, that if you have like x cubed, x to the minus 3, and x to the fourth, that you can combine these together by saying, well, that's x to the 3 minus 3 plus 4. So this would be x to the fourth power, right? Well, we're used to doing that with variables all the time, but it works the same with numbers. I have a 10 to the minus 3, a 10 to the minus 3, and a 10 to the third. So what I'd wind up with is 16 times 10 to the negative 3 minus 3 plus 3 times 5. So I'd have 16 times 5 times 10 to the negative 3. And then I just need to figure out what 16 times 5 is, which that's 80 times 10 to the negative 3. Well, engineering notations, I know negative 3 is milli, so this would be 80 milliwatts. Now, I'm not expecting to see this kind of work. And in fact, when I do these things in my head, I don't do this at all, like write this all out. What I'm trying to show here is that, I can use engineering notation because it's always powers of 3 to kind of cancel things out. You know, I have milliamps, which is minus 3 kiloohms, which is 10 to the third. So like 1 milli cancels 1 kilo. You know, so it's a way to kind of get your units going there. If you're not comfortable doing that, don't do it. Just use your calculator, but make sure, again, to enter things correctly. I see people getting the wrong answer, and it's always because they're entering it into their calculator wrong. Because if you were entering this into your calculator to compute this, you would be entering that the power is equal to parenthesis 4e to the minus 3 squared, because you have to make sure it's squaring the entire term, not just the minus 3. And then times 5e3. Because if you wrote in your calculator, if you type this in your calculator, all that's going to happen, order of operations, it's going to square that first. But it's not going to ever square the 4. The 4 will never get squared and never get made into 16, which is a problem. All right? So, hopefully these are some pretty basic computations for you to do, and there will be some of these on your homework assignment.